In the last video, we took the Maclaurin expansion of e to the x, and we saw that it looked like it was some type of a combination of the polynomial approximations of cosine of x and of sine of x. But it's not quite, because there was a couple of negatives in there if we were to really add these two together that we did not have when we took the representation of e to the x. But to reconcile these, I'll do a little bit of a, I don't know if you can even call it a trick. Let's see if we take this polynomial expansion of e to the x, this approximation, what happens? And if we say e to the x is equal to this, especially as this becomes an infinite number of terms, then it becomes less of an approximation and more of an equality. What happens if I take e to the ix? And before, that might have been kind of a weird thing to do. Let me write it down. E to the ix. Because before, it's like, how do you define e to the ith power? That's a very bizarre thing to do, to take something to the xi power. How do you even comprehend some type of a function like that? But now that we can have a polynomial expansion of e to the x, we can maybe make some sense of it. Because we can take I to different amounts, to different powers, and we know what that gives. You know, I squared is -1, I to the third is -I, so on and so forth. So what happens if we take e to the ix? So once again, it's just like taking the x up here and replacing it with an ix. So everywhere we see the x in its polynomial approximation, we would write an ix. So let's do that. So e to the ix should be approximately equal to, and it'll become more and more equal. And this is more to give you an intuition. I'm not doing a rigorous proof here, but it's still profound. Not to oversell it, but I don't think I can oversell what is about to be discovered or seen in this video. It would be equal to 1 plus, instead of an x, we'll have an ix, plus ix, plus, so what's ix squared? So it's going to be, so let me write this down. What is ix squared over 2 factorial? Well, I squared is going to be -1, and then you can have x squared over 2 factorial. So it's going to be minus x squared over 2 factorial. And I think you might see where this is going to go. And then what is ix? Remember, everywhere we saw an x, we're going to replace it with an ix. So what is ix to the third power? Actually, let me write this out. Let me not skip some steps over here. So this is going to be ix squared over 2 factorial. Actually, I want to do it just the way. So plus ix squared over 2 factorial plus ix to the third over 3 factorial plus ix to the fourth over 4 factorial, and we can keep going, plus ix to the fifth over 5 factorial, and we could just keep going, so on and so forth. But let's evaluate these ix's raised to these different powers. So this will be equal to 1 plus ix squared. That's the same thing as I squared times x squared. I squared is -1. So this is negative x squared over 2 factorial. And then this is going to be the same thing as I to the third times x to the third. I to the third is the same thing as I squared times I. So it's going to be -I. So this is going to be minus I times x to the third over 3 factorial. And then, so then plus, you're going to have, what's I to the fourth power? So that's I to the I squared squared. So that's -1 squared. That's just going to be 1. So I to the fourth is 1, and then you have x to the fourth. So plus x to the fourth over 4 factorial. And then you're going to have plus, I don't even write the plus yet, I to the fifth. So I to the fifth is going to be 1 times I. So it's going to be I times x to the fifth over 5 factorial. So plus I times x to the fifth over 5 factorial. And I think you might see a pattern here. Coefficient is 1, then I, then -1, then -I, then 1, then I, then -1. X to the sixth over 6 factorial, over 6 factorial, and then -I, and then -I, x to the seventh over 7 factorial. So we have some terms. Some of them are imaginary. They have an I. They're being multiplied by I. Some of them are real. Why don't we separate them out? Why don't we separate them out? So once again, e to the ix is going to be equal to this thing, especially as we add an infinite number of terms. Let's separate out the real and the non-real terms. All right, or the real and the imaginary terms, I should say. So this is real. This is real. This is real. And this right over here is real. And obviously we can keep going on with that. So the real terms here are 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And you might be getting excited now. Minus x to the 6th over 6 factorial. And that's all I've done here. But they would keep going. So plus, so on and so forth. So that's all of the real terms. And what are the imaginary terms here? And I'll just factor out the I over here. Actually, let me just factor out. So it's going to be plus I times, well, this is ix, so this will be x. And then the next, so that's an imaginary term. This is an imaginary term. We're factoring out the I. So minus x to the 3rd over 3 factorial. Over 3 factorial. Then the next imaginary term is right over there. We factored out the I. Plus x to the 5th over 5 factorial. And then the next imaginary term is right there. We factored out the I. So it's minus x to the 7th over 7 factorial. And then we obviously would keep going. So plus, minus, keep going, so on and so forth. Preferably to infinity so that we get as good of an approximation as possible. So we have a situation where e to the ix is equal to all of this business here. But you probably remember from the last few videos, the real part, this was the polynomial, this was the Maclaurin approximation of cosine of x around 0, or I should say the Taylor approximation around 0, or we could also call it the Maclaurin approximation. So this and this are the same thing. So this is cosine of x, especially when you add an infinite number of terms. Cosine of x. This over here is sine of x, the exact same thing. So it looks like we're able to reconcile how you can add up cosine of x and sine of x to get something that's like e to the x. This right here is sine of x. And so if we take it for granted, I'm not rigorously proving it to you, that if you were to take an infinite number of terms here, that this will essentially become cosine of x. And if you take an infinite number of terms here, this will become sine of x. It leads to a fascinating formula. We could say that e to the ix is the same thing as cosine of x, and you should be getting goose pimples right around now, is equal to cosine of x plus I times sine of x. And this is Euler's formula. I always pronounce them right over here. And this right here is Euler's formula. And if that by itself isn't exciting and crazy enough for you, because it really should be, because we've already done some pretty cool things. We're involving e, which we get from continuous compounding interest. We have cosine and sine of x, which are ratios of right triangles. It comes out of the unit circle. And somehow we've thrown in the square root of -1. There seems to be this cool relationship here. But it becomes extra cool, and we're going to assume we're operating in radians here, is if we assume Euler's formula, what happens when x is equal to pi? Just to throw in another wacky number in there, the ratio between the circumference and the diameter of a circle. What happens when we throw in pi? We get e to the I pi. E to the I pi is equal to cosine of pi. Cosine of pi is what? Cosine of pi is pi is halfway around the unit circle. So cosine of pi is -1. And then sine of pi is 0. So this term goes away. So if you evaluate it at pi, you get something amazing. This is called Euler's identity. Euler's identity. I always have trouble pronouncing Euler. Euler's identity. Which we could write like this, or we could add 1 to both sides, and we could write it like this. And I'll write it in different colors for emphasis. E to the I times pi plus 1 is equal to, let me get a neutral color, is equal to, I'm just adding 1 to both sides of this thing right over here, is equal to 0. And this is thought-provoking. I mean, here we have, just so you see, I mean, this tells you that there's some connectedness to the universe that we don't fully understand, or at least I don't fully understand. I is defined, by engineers for simplicity so that they can find the roots of all sorts of polynomials as you could say, the square root of -1. The square root of -1. Pi is the ratio between the circumference of a circle and its diameter. Once again, another interesting number, but it seems like it comes from a different place as I. E comes from a bunch of different places. E, you can either think of it comes out of continuous compounding interest, super valuable for finance. It also comes from the notion that the derivative of e to the x is also e to the x, so another fascinating number. But once again, seemingly unrelated to how we came up with I, and seemingly unrelated to how we came up with pi. And then, of course, you have some of the most profound basic numbers right over here. You have 1. 1, I don't have to explain why 1 is a cool number, and I shouldn't have to explain why 0 is a cool number. And so this right here connects all of these fundamental numbers in some mystical way that shows that there's some connectedness to the universe. So frankly, if this does not blow your mind, you have no emotion.